Welcome back to Food Catalyst, and today's class we are going to talk about food engineering problems. Actually, these problems are pretty simple if you know the concepts and how to apply it. So, we are going to debunk some of the famous problems in food engineering and let's understand how the questions are framed in the examination. Okay, so without wasting any time, let's dive into the video. So, the first problem which I am going to teach you is the mass balance. So, before teach you mass balance, obviously I need to explain you the basics, right? So that you can easily understand what is going on in the first place. So, the law of conservation of mass. So, before going to mass balance, let me talk about some important principles under the law of conservation of mass. So, the first principle is mass can be neither be created nor be destroyed. However, the composition of the mass can be altered from one form to another form. Like, what is it? Simply means, see, for example, we cannot destroy or create a mass. If the water is there, you can make it into vapor, right? Or you can make it into ice. You can change the form, but you cannot never destroy the mass. It will just change its form. So that is the very first principle you need to know. So the total system remains unaltered. Okay, so this is the first point. Okay, so let's consider a system. Okay, so I'm considering a system. So in this system, I'm let's say this is a evaporator. Okay, I'm giving some kind of liquid into the evaporator, and that liquid is 1 kg. And whatever it is coming out of it, for example, if it is vapor or the concentrated product or whatever it is, the total of the output should be always equal to the total of the input in an ideal condition. Okay, this is the ideal condition. So how should I interpret this? For example, let me put it in a simple way. The rate of mass entering minus rate of mass exiting. Exiting what? Exiting the chamber, right? This is the system. We can call this as a system. Exiting the system, or like the evaporator or whatever the system we are putting into, right, is equal to rate of mass accumulating in the system. Okay, accumulating in the system. What is that accumulation? That means, for example, what if it is not coming, if the overall product is coming, for example, like 0.9 kg, then the 0.1 kg is actually deposited in the system. Okay, it's accumulated in the system. In certain conditions, we will consider this value to be a 0. Whatever mass we are entering, it has to come exit out of the system. Okay, so to make this in a form of equation, I can say m inlet. Okay, m inlet minus m exit, which is equal to some of the some mass has been accumulated in the system, right? But that is very small mass. As you can see, it is very, very small. So dm per system depends on the time also, right? If for example, if the evaporator is running for a long time, we can expect little bit of mass deposited here and there. So it's depend on the time. So that's why dm system divided by dt. Here this mass is deposited on the system. Okay, so see how to calculate this inlet. First of all, it's pretty simple. Why we are not directly giving 1 kg, right? In an ideal situation, we are pumping the liquid, so we have to say 1 kg per hour. So means for every hour we are calculating that at least 1 kg liquid will be entering into the system. So to calculate the mass inlet, you can say that it's a summation of overall mass. It's a summation of overall mass mi, where the I means inlet. Okay, so where the I can be 1 to all the way to n, like how much of liquid has gotten into. That's it. This is the simplest equation of law of conservation of mass. Okay, now we have to, like, let's say, use this basic idea and apply it in two systems. One is called as open system, okay, and another one is a closed system. I'll explain that, okay, no issues. I'll explain this concept in a simplest manner. Okay, so before explaining it, you need to know one thing: vector quantity. What is a vector quantity? Vector quantity is one thing which has both magnitude and direction. Okay, for example, if the liquid is flowing, then it is moving in this direction, positive, reverse direction, negative. So magnitude and the direction is the vector quantity, and I'm going to calculate what the velocity of the liquid. So the velocity is actually a vector quantity. So okay, so I'm considering the same principle here, where I'm taking I'm taking a evaporator, let's say, and I'm flowing the liquid, and it's coming out of the tank also, and I can say this liquid is flowing in this direction. Okay, I'm mentioning the velocity as u, and I'm putting the direction here. Okay, so this is the open system, where the system is open to enter and exist. Okay, so you can put a mass, that mass can enter and that mass can exit. So it's an open system. Okay, like you are getting the point, right? But here is a like important point. See, in this open system, you have to consider a small mass to calculate the speed of how much of velocity is there. For example, a small amount of mass is moving. Okay, for example, imagine the pipe and you are calculating a small distance. This is dm. Mass is equal to what? Density into velocity, okay, speed of the liquid, into the small distance. Okay, first of all, the p is the density of the liquid, because if the liquid is denser, then obviously you cannot like make the liquid go faster, right? For example, honey will go slower compared to water because of the density. So first, this dm is the small amount of mass flowing in. Okay, flowing in. And what is this? This is the density. And along with this u is the speed of fluid. Actually, which is perpendicular. Right? This is perpendicular. Which is perpendicular to open. And dA is what? Tiny area where liquid is flowing. So that's it. This is how you need to calculate a open for example, this is how you need to calculate an open system. Done. Now let's calculate a closed system. Okay, first of all, you need to consider a closed system, right? So I am taking an example. See, in this closed system, mass is present, but the mass is present inside the system. But it cannot leave the system. So the mass remain unchanged. Okay, what does this mean? Simply means, take this as an example, canning. After you put all the ingredients in the can, you are heating it, but since the can is very much sealed, Since the can is very much sealed, the mass is not flowing in or out, or not flowing out. This process is not happening. Here the mass is constant and it does not vary with time. So this DM, it will not separate because the mass will not change, right? It will not deposit or accumulate, or it will not do nothing. This value is 0 in case of closed system. So in closed system, dm by dm system divided by dt is equal to 0, because obviously the total mass remain constant with time, because you are just heating. There is no leaving of mass here. Okay, mass is not coming in or not going out, so the process is not happening. So the mass transfer is not happening. So here whatever the mass you are seeing will be constant. So that's it. This is the basic you want to know to solve some problems. Okay, now you understood the basics of mass balance. Now let's try to solve some questions. So the first question is, how much of dry sugar you must be added in 100 kg of aqueous sugar solution in order to increase its concentration from 20 to 50%. Okay, so first of all, let's debunk this question. I have a 3-step method to follow it and solve every single problem. The first step of the solution is to draw what is asked in the question. What does that mean? Simple. See, you have to consider all this as a system, which I have talked about earlier. You have to consider everything as a system. So let's read that question again. How much of dry sugar is added? So we are adding dry sugar. I'll mention that as S. Okay, is added into 100 kg of aqueous sugar solution. Actually, we are adding sugar into a solution to increase this concentration to 20 to 50. So actually we are adding a sugar into a sugar solution. Means actually we are mixing it. We are doing the mixing operation. Okay, and how much I am adding? I am adding 100 kg of aqueous sugar solution. And when it get out, how much of concentration is increased from 20% to all the way to 50%? It's increased. And because of what? I'm adding some dry sugar. Why I'm pointing this arrow here? Because this two things has been added and mixed, and we got out this 50% of concentrated sugar. So this is the first step of how to solve this. So basically, to make this a little more easier, I'm going to give some name to these three processes. So the first one, let me name this as S1, and in the second one I'm going to name it as S2, and the third one I'm going to name it as S3. So I'm adding S1, S2 and mixing, I'll get an S3. So this is what I'm getting from the question. So first step is done. This is step 1 and it's done. Let's do the step 2. Step 2 is to do a mass balance. So what is step 2? It's a mass balance. We are balancing the mass, because here the question is asking the mass of the dry sugar. So in this way you can understand we have to do a mass balance. Okay, so how to do a mass balance? It's simple. This is what we have talked about earlier. See, in a system, whatever we are adding it, okay, whatever you are putting in the system, you are going to get the same out of the system. So the inlet is equal to outlet, right? So that's what we are going to do. So in this one, we are adding S1 and S2, right? So S1 plus S2 is equal to S3. Okay, so what is the mass? You don't know mass of S2 and S3, but you know the mass of S1. S1 is 100. S2 I don't know, it's some sugar. I need to calculate the S2 only. S3 also I don't know how much is the output which I am getting, right? So S3. So what happened is, here you made a equation. You can call this equation as a let's say equation number 1. Okay, let's keep that equation. Now what you have to do is, what is the second thing which is given? It is given concentration. See, you can see this concentration as a solute, right, or solids. I can say this as a solid. Why? If I'm telling you, this is a simple examination. If I have 100 kg of solution, in that 100 kg solution I have 20% concentrated sugar. That means in that 100 kg 20 kg is sugar. That's what the concentration means, right? So if I apply that principle here, if I apply that same principle here and do the mass balance again, this is the mass balance, okay, for solids. Here this mass balance contains total solids and liquids, because in the 100 it contains solids and liquids both. Now I am going to compare only solids. But how to do it? Simple. In that 100 kg, 20% means 20 divided by 100 is the amount we need. So 100 into 20 divided by 100. And S2 we don't know, right? We don't know how much of S2 we need to give. So it's just S2. S2 is simple sugar. We don't have any other data related to S2. And S3. S3 also we don't know, but we know the concentration is 50%. So it's actually 50 divided by 100. So this is what I'm getting in a second equation. If I solve this, what happens is I'll get 20 plus S2 0.5, right, 0.5 S3. This is the second equation. So what I have is, I have two equations and I have two variables. So I can solve this equation. Okay, I can solve this two equation. I can substitute this to the equation and I can get the S3. Once I get the S3, answer is actually 160. I have to apply into the S1 and it's actually 100 plus S2 is equal to 160. So S2 is equal to 160 minus 100 and S2 is equal to 60. So if you don't know how to solve this 1 and 2 equation, I'll do it for this one problem, okay? Rest of the problem you have to do it. So it's actually see, 20 plus S2 is equal to 0.5 into S3, and here 100 plus S2 is equal to S3. Okay, so I can put minus minus minus. Okay, are you getting the point? I can put minus 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 in the lower section. It will cancel out and it will get 80, and plus or minus will cancel out, and 1 here is 1 is there, here 1.5 is there, so it's actually 0.5 S3. So 0.5 S3 is nothing but 1 by 2, right? 1 by 2 S3. So this 2 will go here. 80 into 2 is equal to S3. So S3 is equal to 160. So that's how I got 160, and I'm applying it in the first equation and I'll get 60. So that 60 is the S2. So what I need is S2. S2 is 60. Now 60 kg of sugar has to be added to make it to 20 to 50%. That's it. Now I have completed the first question. Let's move on to the let's say a little difficult question. Okay, so in this question, see, the question might be difficult, but once you have made the diagram out of it, then it will be easy. Let me tell you how. First step is what? Draw. So first step. So let's read the question. A fresh orange juice with 12% of soluble solids is concentrated to 60 in a multiple effect evaporator. To improve its quality of the final product, the product concentrated juice is mixed with the amount of fresh juice cut back so that the concentration of the mixture is 42, and calculate how much of water per hour must be evaporated in an evaporator and how much of fresh juice per hour must be added back. Okay, so this is lot to process, but I'll let you know in a simpler manner. Okay, so what happens is I'm actually evaporating the juice. That's the question. Okay, and what juice? It's an orange juice. Okay, so when I have to draw a system, now the system is actually evaporator. Okay, so I'm I'm adding the fresh juice in, and how much of fresh juice is there? It's in the question end. How much of final product is produced if the inlet feed is 10,000 kg? So actually the inlet feed is 10,000 kg per hour. Okay, so I know the value of inlet, and how much of concentration from 12 percentage to 60 percentage. Fresh juice of orange with 12 percentage of soluble salt is content is concentrated to 60. So here it is 12 percentage. When it comes out of it, it is actually 60. But the question is not ended here. To improve the quality, they are actually mixing it further with the fresh juice. So I'm again adding a new system, and the system is actually mixing system. Okay, and in the system what happens is, see, this is important. See, I have forgot to put one thing. See, while evaporating, water is actually removing, so water is actually going out, so I'm putting the arrow mark outwards. Okay, not inwards, it's outwards. Okay, so water out. And see, in the mixing process, what I'm doing is I'm adding a fresh juice back. Why? To get the concentration to 42. So the final concentration is actually 42, and I'm adding a fresh juice. You know, fresh juice concentration is 12 percentage. So 12 percentage. You don't know the value either. Okay, you don't know the value either. So first, we need to assign some factors to calculate this. So to simply put water, I'll put W. Okay, so water W, and how much of coming out from the first system, I'll put X, because I don't know X. And the fresh juice we are adding at the second time, we don't know how much of fresh juice we are adding, so it is F. It is not 10,000 because only the inlet feed is 10,000. You cannot put 10,000 here, but the concentration of fresh juice is same. Okay, that's why I'm not putting 10,000 here. This is important. Okay, so here F, I'm putting F, and I'm getting some product out of it. So I can say this final product as Y. Okay, let's keep that Y. Okay, now you have drawn the picture. See, I can actually divide this into a two system. It's not just one system, right? In the first system, it is actually cutting here. This is his second system. So actually you have to solve the questions in a two system manner. Okay, system 1 and system 2. If you have divided this, then the question will be much easy. Okay, what is the second step which I told you? It's mass balance. It's mass balance. Okay, to do the mass balance, let's do in the first system first. Okay, so mass balance of first system. So first system, whatever I'm like inserting it is actually 10,000. Okay, plus along with, sorry, only the water I'm putting, only the juice I'm putting in the evaporator one, and what I'm getting out is actually water plus X. Okay, so if I use the same concept of asking the soluble solids of the first system, then what happens is the same 10,000, okay, into how much percentage? It is 12 percentage. So 12 divided by 100 is equal to water. Actually, see, this is the point. If we don't know water, how much of water, but the concentration is water is what? 0, right? There is no solids in the water. So it's actually 0 divided by 100. Because we are only comparing soluble solids. In water, there is no solids. So 0 divided by 100 plus X, we know X is 60. So 60 divided by 100. So this is what I'll get in the first equation. One is 10,000 is equal to W plus X. In another one, I'll get cancel. this whole thing will be cancelled and cancel. I'll get what? 120. I'll write it here. Sorry, 1200 is equal to x into 6 by 10. Okay, I can make the 10 go here. Thus 1200 is equal to x6, and if I cancel the 1 and 2, it is x is equal to 2000. I got the x, I can substitute the x here, and I'll get the w. Okay, if I 2000, if I minus the 2000 with the 10,000, you'll get the 8000. Now I got two values. What? I get 8000, which is amount of water which I'm actually getting out of it, and I'll get the x. The x is actually 2000. I know the inlet of the second equation. Now do the mass balance in the second equation. I already know 2000 is there. So 2000 plus, I am adding f. I don't know how much f we are adding. F means a fresh juice, right? And I am getting y out of it. Okay, I am getting a y out of it. So in this one, let's do the same mass balance of soluble solids. So we can say 2000, and in the soluble solids it is 60%, right? 60 to 42. So first is 60%. So 60 divided by 100, because the inlet value is 2000 and it is 60%. So 2000 into 60 divided by 100 plus f. F is actually 12%. So f into 12 divided by 100 is equal to y is how much? Y is actually 42%, right? So it's 42 divided by 100 into y. So I'll get two equations. This is the equation number 1 and this is the equation number 2. So just simply cut down all the values and solve the equation. You will get what? Again you have to solve all these equations. Ultimately you will getting a value of f, which is the fresh juice which you are going to add, is as 1200. Once you get the value of f, you have to add back to the, as I told you how to solve this equation, right? Just like I did it here. Once you got the equation, you have to like solve the equation. Okay, so once I get the f out of it by solving the first and second equation, I have to add back into the first one. So it is 2000 plus 1200 is equal to y. So y is equal to 3200. So final output product is actually 3200, and the fresh juice I'm adding is 1200, and the water which is removed is 8000. So I have answered all the questions which is asked. Done. Now we have done with two important questions in mass balance. Okay, so let's move on to the third and final question. So this is an easy question. Okay, so the question means it looks difficult, but let's solve this question. What's the first step? To draw. So let's draw. So 100,000, this is the kg of fruit juice with 10% solids is freeze concentrated to 40. Now you know what is the first step, right? This dilute juice is fed into the freezer. Okay, that where the ice crystals are formed, then the slush is prepared in the centrifugal separator into ice crystals and concentrated juice, and the amount of 500 kg of liquid is recycled from the separator to the freezer. Okay, so this might seem complicated, but let me break it down. First of all, let's start with the first one. We know inlet is actually 10,000, okay, and 10% solids. And what I'm doing an operation called freezing. But I'm not just freezing. In the second line, and they are telling that the dilute juice is fed to the freezer where the ice crystals are formed. Then slush is separated. in a centrifugal separator. Then after freezing, they are adding it into a separator. Then I am getting the concentrated juice. It's actually freeze concentrated, means first freezing then concentration. So this combination of these two, I am getting the 40%. So it's a combination of two systems. Okay, the 10 to 40 is actually from here to here. Okay, done. What happens is, once they to make this into a equal state, if any slush is properly not slush, then this they are feeding back 500 kg per hour. Actually, they are actually recycling this to the freezer. Now what they are asking is amount of ice is removed in the separated. Okay, see, in this separator ice is actually removed and I am getting the concentration. Obviously, right, if you are concentrating from 10 to 40%, you have to remove some moisture out of it. That is, we are removing it as ice because we are doing freeze drying. So you need to calculate this ice. That is the question. See, this question is very simple because they have given a extra information of recycling. This information is not needed. Why? Basically, it's a simple step. Let's do the mass balance first of all. Let's do the mass balance, then you will understand. In this mass balance, the inlet is actually 1,000, sorry. Okay, inlet is 1,000. What is the exit? Is actually 40 and 10. Sorry, 40% is the output, which I'm going to mark it as the juice. Okay, simple. The juice plus I'm getting ice out of it. Ice. This interior process is not needed because it is within the system. It's a closed system. Okay, this since it is not going out of the system, it is within the system. We should not need to calculate it. Okay, you are wondering how this happened, right? Let me rephrase it in a way so that you can easily understood. Recycled stream. Okay, recycled stream does not affect the result. Does not affect the result. Why? Only the streams that cut the envelope or cut the system. For example, this ice is actually cutting the system. This is not cutting the system. This ice is cutting the system. So only the streams which cut the system take part in mass balance. In mass balance. Do you got it? Whatever it is cutting the system, they had to take part in the mass balance. Whatever happening inside, it is inside. So no issues. You don't need to calculate it. So basically, if you apply the mass balance of solids, it's actually 10,000. 1,000 into 10% means 10 divided by 100, which is equal to ice. Ice, what is ice? Like, it's 0 divided by 100, right? There is no solids in ice. As you can say, it is a solid, but no. We have to say the concentration is the solutes, which we can say. Solutes, there is no solute in the ice, right? So it's 0 divided by 100 plus it's actually juice, which is 40 divided by 100. This we will cancel out. We'll get 100 equal to J 40 divided by 100. So once you have solved it, you will get J is equal to 250. If you know the J, use it here. What is will be the 250 minus 1000? It's ice is 250 minus juice is 250 and this is 1000. So ice is actually 750. Yeah, it's 750. So 750 kg per hour. It's the value. Answer. It's actually a simple question. I didn't even take much space. but the question is big. And that's how they will trick you. So this kind of questions may ask in the patent examination. So if you are writing for a patent examination, this is how you need to study it. Okay. So that's it for this video. So in next video, we're going to discuss about the moisture content and their related problems. So make sure to stick on to the video and watch the video till the end so that you can understand the problems. Thank you.